While playing with the ball, Nora gets curious about its motion. As she drops the ball on the floor, she asks herself, what will be its speed as it reaches midway in its path? She drops the ball from a height 1 meter above the ground. It covers 50 centimeters to reach the midpoint. Nora knows that it took 1 second for the ball to reach the midpoint B. With this information, can she find the speed of the ball exactly when it's at point B? Like you'd probably be thinking, Nora also thinks the speed of the ball will be the distance traveled by it divided by the time taken to reach that point. So she comes up with the answer 50 centimeters per second or 0.5 meters per second. But is this the speed of the ball when it's at point B? No, it's not. This answer would have been correct if the speed of the ball was constant throughout its motion. But we know that the speed of the ball increases as it falls. So, the answer Nora got is actually the average speed of the ball as it reaches the position B. But what we are interested in is the speed exactly at the instant when the ball is at position B. That is called the instantaneous speed of the ball. Can you try finding the instantaneous speed? Let's see what happens at the instant the ball is at position B. The distance traveled by the ball at this instant is 0 and the time elapsed at this instant is 0. So we get the speed to be 0 divided by 0, which is undefined. Doesn't make any sense, right? So how do we then find the instantaneous speed of the ball? Calculus is the branch of mathematics that helps us answer this question. How? We will see that in the later section of this course. But wait, another thought puzzled Nora. As she drops the ball, she wonders why the ball ever reaches the floor. This might seem to be a lame thought, but don't forget that Nora's smart. She thinks that mathematically, the ball should never touch the ground. So what was her thought process? Let's see. Suppose she drops the ball from a height 1 meter above the floor. Now to reach the floor, first the ball has to cover half this distance to reach point B. Then the ball has to cover half of the remaining distance, that is 1/4 of a meter. Then the ball has to cover the next half, then the next half, and so on. It means the number of steps the ball has to cover to reach the floor does not end. That is, there are infinite number of steps the ball has to perform. And to perform these steps, the ball takes an infinite amount of time. So according to this logic, Nora thinks the ball requires an infinite amount of time to reach the floor. Therefore, the ball should never reach the floor, right? Do you also think the same? Do you think Nora went wrong somewhere? Actually, Nora isn't the only one who was puzzled by this. Many centuries ago, the same thought puzzled a Greek philosopher, Zeno of Elea. This is usually referred to as Zeno's dichotomy paradox. Even though we know that when we drop the ball, it reaches the floor, this logical and mathematical conclusion tells us that it should never reach the floor. Again, a satisfactory answer to the Zeno's paradox is provided by calculus. We saw 2 examples here that calculus can give us the answer to. But before looking at the central ideas of calculus, we will further explore what other real-life problems calculus can help us with. If we're on a cliff next to the sea, it's always tempting to randomly throw stones into the sea. It's so much fun, right? But have you ever wondered about the best possible way to throw a stone such that it covers the maximum distance? Knowing this was certainly important in the past to attack the enemy's ship. Now, let's get back to our question. If we throw a stone too high, we know it will not cover maximum distance. What if we throw the stone horizontally? Maybe not. By experience, we know instead of throwing the stone horizontally, if we throw it at an angle, it will cover greater distance. Of course, the answer also depends on the speed with which you throw the stone. Let's say if you apply all your energy, you can throw it with a speed v. So if we throw the stone with a speed v, at what angle should we throw it to cover maximum possible distance? As the angle at which we throw the stone changes, the distance covered by it changes. And this is where calculus comes into play. To get the answer, we need to know how the distance covered by the stone changes as the angle we throw it at changes. And this is exactly the kind of problem that calculus helps us with. Alright, so calculus helps us with analyzing things in motion. For instance, finding the instantaneous speed of an object or finding the angle at which to throw the stone. But wait, let me ask you a completely random question. Look at this trajectory of the stone. What do you think will be this area under the dashed curved path? We know how to find the area of a simple shape like the rectangle. Its area is equal to its length times its width. But how do we get this formula? Let's say the length of the rectangle is 5 centimeters and its width is 10 centimeters. Then the area of the rectangle is 50 square centimeters. So what does this mean? It means that if we take a square tile of length of 1 centimeter, that is a square tile of area 1 square centimeter, then 50 such tiles will cover this rectangle. Now let's get back to our question. What will the area be under this curve? Should we cover this area also with square tiles? This will not work right. Look at the square tiles covering the curve. We have a problem here as they don't fit perfectly. Then how can we figure out this area? You would have guessed by now that calculus helps us to find the answer. We know the area of simple shapes like rectangles, triangles, polygons, and so on. Here are the formulas. This is easy because straight lines are involved. But the shapes that we encounter in our daily lives are not that simple as curves are involved. That's where calculus comes into the picture. So we've seen that other than finding the instantaneous speed of an object and the angle at which to throw an object to cover maximum distance, calculus also helps us to find the area of different shapes. In this course about calculus, we will explore each of these examples in detail. But before moving on, let's have a glimpse at the central idea around calculus. This idea was used by Greek mathematicians to find the area of a shape long before calculus was developed. Consider this circle with radius r. How would you find its area? Consider these two triangles. One circumscribed around the circle and the other inscribed inside it. We can say that the area of the circle will be between the areas of these two triangles. Now, what if we used squares instead of triangles? We will get a better approximation of the area of circle if instead of triangles, we used squares. We can further improve our results if we used pentagons. Did you get the idea? Can you tell me how we can improve the approximation further? As we consider polygons with greater number of sides, we will get close to the circle. The area of the polygon inscribed in the circle and the area of the polygon circumscribing the circle get closer to each other. This was the method used by Greek mathematicians to find the area of the circle. It's called the method of exhaustion. This is the central idea of calculus used to solve the problems we mentioned above. With this knowledge, do you think we can solve our problem of finding the instantaneous speed of an object? Think about the ways in which you can approach the problem. Do you know which is the hardest mountain to climb? You would probably say Mount Everest since it's the highest mountain. But that is incorrect. The hardest one is the second highest mountain, K2. Due to the difficulty of its ascent, it's called the Savage Mountain. It is harder to climb K2 because we know that along with height, there are many other factors to consider. Steepness is one of them. For example, let's consider these two mountains. The right one clearly has more altitude, but the left one will be harder to climb as it's steeper. Now let me ask you a question. What do we mean by steepness? For example, consider these two straight lines. Which one is steeper? Here the difference is subtle, but we can see that it's the second one. But can you think of a way to concretely prove that the second one is steeper? One simple way is to draw the horizontal and vertical lines like this, measure their lengths, and find the ratio of the vertical length to the horizontal length. On substituting the values, we get 1 and 1.5. The second ratio is clearly greater. What does this tell us? If we walk along these lines, this ratio tells us how much vertical distance we cover relative to the horizontal distance. So if the ratio is higher, it means that the slant line is steeper. We can also see this as the distance covered while going up per unit of the distance while going across. There's another way to know which line is steeper, and that is to find this angle. Greater the angle, steeper will be the line. But notice that these two lines are connected to the angle by the trigonometric tangent function. This ratio is equal to tan theta 1 and this is equal to tan theta 2. Such a ratio for a straight line is called its slope. It's the measure of the steepness of the line. Now look at this curve. What is the slope of this curve? Does it even make sense to ask this? What do you think? In this video, we'll understand what this means. Here, the process of differentiation helps us. Also, we know that such a curve can be represented algebraically by a function between two variables. We will see that this slope is connected to the idea of the derivative of a function. So let's continue with our question. One thing we can clearly see here is that different positions of the curve will have different steepness. We can intuitively see that as we move from the left towards the right along the curve, it gets steeper. So the slope of the curve in general doesn't make sense. So let's focus our attention around this point P. What will be the slope at this point? For this, let me ask you one question. Is the earth flat or round? You'd probably be laughing because we all know that the earth is almost round in shape. But notice the surroundings around you. It seems that the earth is flat. Why is it so? Consider this circle as the representation of the earth. And let's say you are currently situated here. If we zoom in around this portion of the curved line, we see that it becomes less and less curved. It looks almost like a straight line. So let's say we draw a straight line only intersecting the curve at this point. We can see that the curved line is almost the same as this straight line. We know that this line, which passes through only one point of the curve, is called the tangent line at that point. Take a moment and just observe what we found. This is the most important idea on which calculus is built. A curved line in a very small region around a point on it can be approximated by a straight line. This straight line is the tangent line at this point. So this solves our problem. The slope of the curve at a point will be equal to the slope of the tangent line at that point. And we are familiar with how to find the slope of a straight line. So how do we find the slope of the tangent line at this point? Lastly, we saw what we meant by a function between two variables, x and y. A function tells us how the value of one variable depends on another variable. So if the value of x changes from x0 to x0 plus delta x, then the value of y will also change from y0 to y0 plus delta y. Now look at this ratio, delta y over delta x. It tells us the rate at which the value of y changes in proportion to the change in x. For example, consider these two ratios. As the ratio in the second case is greater, the value of y will change relatively faster here. This rate of change for a function is actually related to the slope of a curve. Let's see how. Let's say the graph of this function is a straight line like this. x0, y0 is this point, and when the value of x changes by delta x, we reach this point. Now consider the ratio delta y over delta x. We saw earlier that for a straight line, this ratio is the measure of its steepness. So, the rate of change in y with respect to x is equal to the slope of this line. Now we can see that for a straight line, its slope is constant throughout. So its rate of change will also be constant. But what if instead of this, the graph of the function is given by a curved line? The slope at a point tells us the rate of change at that point. We've seen earlier that in a very small region around a point, the curve can be thought of as a straight line. This is the tangent line at this point. So we see that the slope of this line is equal to the rate of change here. But now, we can see that depending on the point on the curve, the slope will change. So this means, depending on the value of the x variable, the rate of change will also vary. Now let's look at an example to understand this. Let's say in this function, y is the distance traveled by an object in motion, and x is the time taken for the distance traveled. Then the rate of change in y with respect to x will be equal to the speed of the object. In the first case, we know that the rate of change is constant. So the speed of the object will be constant throughout its motion. While in the second case, the rate of change is not constant. So here, this rate will tell us the instantaneous speed of the object. For this reason, the rate of change for a function at a particular value of x, x0 is called as the instantaneous rate of change at x0. So to conclude, a very small portion of a curve around a point can be approximated by the tangent line at that point. The slope of this tangent line tells us the instantaneous rate of change of the function at that point. But how do we find this slope or instantaneous rate of change? Do you remember that in one of our previous videos, we found the instantaneous speed of an object? To find the instantaneous speed, we have to use the process of differentiation. Let's say we want to find the instantaneous speed at this point P, that is at the time instant x0. For this, we first find the average speed for some time interval delta x. At x0, the distance covered will be this. And at x0 plus delta x, it will be this. So the average speed in the time interval delta x will be equal to this. For a function, this ratio is called as the average rate of change. Now let's say we draw a straight line between these 2 points. It's called the secant line. We see that the slope of this secant line will be equal to the average speed in the time interval delta x. So we see that the average rate of change between 2 values of x is equal to the slope of the secant line between the corresponding points on the curve. Now what's the next step? How do we find the instantaneous speed from this average speed? For this, we find the average speed in shorter time intervals, that is, as delta x tends to 0. We say that when the limit delta x tends to 0, the average speed approaches the instantaneous speed. This instantaneous speed is the instantaneous rate of change at x0. Now what happens to this secant line as delta x tends to 0? Let's say we find the average rate of change between points P and Q1, Q2 and so on. We can see that as delta x tends to 0, these points come closer and closer to the point P. So as the limit delta x tends to 0, the secant line will pass through only one point P on the curve. That is, the secant line approaches the tangent line. This is how, using the process of differentiation, we find the instantaneous rate of change of a function or the slope of a tangent line. Now here, instead of writing the instantaneous rate of change in y with respect to x at x0, we say that the derivative of the function at x0 is this. The derivative is usually denoted by the symbol dy by dx. So we saw here that the derivative of the function at a particular value of x is its instantaneous rate of change at that point. Derivative of a function measures its rate of change. Imagine a quantity denoted by variable y which is continuously changing. But how it changes is controlled by another quantity denoted by variable x. We can say that the variable y, called the dependent variable, is a function of the variable x, called the independent variable. The function f tells us how the value of y changes with the value of x. The derivative of a function at a particular value of x tells us the rate of change of y with respect to x at that particular value of x. That is how fast or slow the value of y changes with respect to x. In our previous video, we saw how to find the derivative of a function. The whole process is summarized like this, and it's called differentiation. This ratio here is called the average rate of change between two values of x, which are x0 and x0 plus delta x. If delta x is greater than 0, then x0 plus delta x will be somewhere here on the x-axis. Then this ratio is the slope of the secant line between these 2 points. Now, as we find the average rate in the interval closer and closer to x0, we see that these secant lines approach the tangent line at x0. This would be true even if we take delta x to be less than 0. Then x0 plus delta x will be somewhere here on the x-axis. And as we find the average rate in the interval closer and closer to x0, we see that these secant lines approach the tangent line at x0. So we say that in the limit delta x tends to 0, the average rate of change approaches the instantaneous rate of change at x0. That is nothing but the derivative of the function at x0. We denote it by putting dash like this on the notation for the function. Note that the limit delta x tends to 0 does not mean we put delta x equal to 0 in this ratio. This would result in the ratio being equal to 0 divided by 0, which does not make any sense. In this video, we will understand what this really means. Along with it, we will also explore different theoretical aspects of the derivative of a function. Consider this simple example. Y is equal to square of x. Let's say we want to find the derivative of this function at a particular value of x, say x1. Can you find this out? Actually, in one of our previous videos, we found the answer to this. We had found the instantaneous speed of an object for such a relationship between the distance traveled and the time elapsed. To find the derivative, we would first find the average rate of change. That is, how the value of function changes as the value of x changes by delta x. F of x1 plus delta x and f of x1 will be equal to this. After expanding this term and simplifying, we will get this. And after dividing by delta x, we will get this final expression. Now we know that to get the derivative, we will need to consider the interval delta x tending to 0. So we put delta x equal to 0 here and get this. It's the derivative of the function at x1. But now notice that all these expressions are equivalent to each other. So what if instead of putting delta x equal to 0 here, we put delta x equal to 0 here or here? We see that we will get the numerator and the denominator both equal to 0. But for this final expression, we got the answer as 2 times x1. So what's going on here? Why can't we substitute delta x equal to 0 here and not here? Actually, substituting delta x equal to 0 at any step here is not correct. Notice that in these steps, we are dividing by delta x. And we know we can't divide by 0. What delta x tends to 0 means is that we are considering smaller and smaller values of delta x. The values of delta x are close to 0, but never 0. But among all these steps here, delta x does not explicitly occur in the denominator here. So it's easy to see from this step that as delta x gets smaller and smaller, the average rate gets closer and closer to 2 times x1. So substituting delta x equal to 0 here is just convenient to reach this conclusion. But always be aware of what it really means to put delta x equal to 0 here. Now notice one more thing. Although we had not explicitly stated here we took delta x to be greater than 0. That is, we are finding the average rate between x1 and the values of x greater than it. But it is necessary to consider the case when delta x is less than 0. That is, finding the average rate between x1 and the values of x lesser than it. As we find the average rate when delta x tends to 0, this average rate should approach 2 times x1. So let's find the average rate in this case when delta x is less than 0. We can see the calculation for finding the average rate of change will be the same as this. But in the first case, this average rate will always be greater than 2 times x1. And in the second case, this average rate will always be less than 2 times x1. Now when delta x tends to 0, both these average rates will approach the same limit 2 times x1. Now we can conclude that the derivative of this function at x1 is equal to 2 times x1. So we see that to find the derivative of a function at a particular value of x, we have to find the average rate of 2 cases. When delta x is greater than 0 and when delta x is less than 0. Now when delta x tends to 0, if both these average rates approach the same number, then that number is the derivative of the function at that particular value of x. But consider this function now. It's called the absolute value or modulus function. These vertical bars say that the value of y is equal to only the non-negative value of x. That is, if x is greater than or equal to 0, then y is equal to x. And if x is less than 0, then y is equal to negative of x. Can you find the derivative of this function at x equal to 0?